Okay, so let's start with our first section of notes. This is going to be over planet Earth and the Earth's interior layers. So we're going to talk about those interior layers. We're going to talk also about the appearance of Earth and how it's changed over time, and then also what geological features we can find at plate boundaries. So the first one is going to be let's focus on the Earth's interior. And what we know about the Earth's interior is that it's made up of several distinct compositional layers, meaning that there's going to be distinct layers within the Earth that are different from each other. The crust is going to be the outermost layer. It's thin, it's solid, and it's going to be just above the mantle. We know a whole lot about the Earth's crust because of what this is the layer in which we live on. Underneath the crust is going to be the mantle. That's the layer of rock that's found between the Earth's crust and the core. You can see the picture here. The crust is going to be the outermost layer. The mantle will be then that yellow layer. And then we'll talk about the outer core and the inner core. When we talk about the Earth's interior, the deeper down that we get, the more warm those layers are. A lot of it's due to the pressure in which those layers are under. A lot of the metals that make up those layers are actually starting to become more liquid like in nature. When we talk about the core of the Earth is going to be the center part of the Earth, just below the mantle, and it's classified into two different types. We have the inner core, which is thought to be solid and made up of solid metals, and then we have the outer core, which is thought to be more of a liquid in nature. Uh, those two are going to be mostly comprised of nickel and iron that has melted over time. Okay, the Earth's interior also is radioactive due to the high internal temperatures. What happens is the radioactive isotopes are constantly being broken down: uranium, thorium, and potassium. This then gives off energy that then contributes to the Earth's high internal temperatures. The mantle is going to be about 1,250 degrees Celsius, while the core can be over 5,000 degrees in temperature. When we talk about how the plates on the Earth have changed over time, uh, that's how we focus on the appearance of the Earth and how it's changed over time as well. And that all comes down to Alfred Wegener. Okay, Alfred Wegener came up with the idea that of continental drift. This stating that all of the continents may have at one point been one large landmass and have thus broken up since then and drifted apart, giving us our seven continents that we have today. What Wegener believed was that at one point all of these continents were joined together. And he called this the supercontinent, which is known as Pangaea, or what he called Pangaea. He supported this idea with fossils that he found on several different continents. They seem to be similar in nature, and thus, what Wegener came up with was the idea that those animals can't swim across the sea, and thus must have come from the same place, and those continents thus must have joined together or been joined together at one point in time. So you can see kind of here is some drawings showing how that continental drift or the changing of our Pangaea breaking apart into the continents that we have today. Pangaea, you can see, took place or was around in the Permian area of time, and then it over time it's so slowly but surely those continents and their plates have changed, breaking apart into what we have today as our present day globe. So, although Wegener thought that fossils were enough evidence to support this idea, more evidence was found later on when we examined the ocean floor more in structure, and we're able to find that the ocean floor actually gave us symmetrical bands that were forming on either side of what we called the mid-oceanic ridge. And those bands then indicated that the two sides of the ridge were actually moving away from each other or pushing away from each other, and new ocean floor was rising up in between them. So, thus supporting the idea that these plates were actually moving throughout time. the alignment of the oceanic rocks supports this theory of plate tectonics. You can see with that red line down the middle, that'd be the mid-oceanic ridge. And on either side of that mid-oceanic ridge would be those symmetrical bands, suggesting that the rock or the crust was being formed and then pushing away from those, thus moving our continental plates, or those big plates that are outlined in black on the picture. And what happened was as the magma would start to cool on the ocean's crust, that iron in the molten rock would then align, and it would actually give us little stripes, and it would align due to the magnetic fields that the Earth has in the positive and negative poles that we have. So the plates have moved over time over the mantle. The crust and the upper portion of the mantle are thought to have be divided and giving us our 7 large pieces, which we call our tectonic plates. This layer of the crust in the upper portion of the mantle is thought to be, or is called, the lithosphere, the solid outer layer of the Earth that consists of the crust and the upper ridge of the upper part of the mantle. It is this region, the lithosphere, that is thought to do all of the moving. The plate tectonics, then, is just the theory that explains how this lithosphere and those plates have changed over time and shape and moved into the places that they currently are today. So what you can see here in the picture is we have 2 different crusts. We have continental crust and we have our oceanic crust. Both are going to be found in the lithosphere, so that'd be the crust itself up here, and then the upper part of that mantle in which those plates are able to move. And this picture shows the different ways in which the Earth is currently moving. You can see those arrows point towards the direction in which the plate is currently moving or was moving and pushing up against each other. And so what you can see is along some of those boundaries, there's going to be different regions that will form, like mountain regions, or as they move away from each other, that's where we will find our ridges within the ocean crust as well. So this convection currents, scientists believe that these convection currents that are located in the asthenosphere, which is directly below the lithosphere, almost act as the layer in which the mantle can move. So it's usually going to be made up of a hot fluid portion of the mantle that allows for those plates to glide and easily move over. So it's almost like the wheels on a car allowing for it to move. So what can we find at these plate boundaries? What type of structures can we find? Well, we can find both volcanoes and earthquakes, mountain ranges as well, and then rift valleys also can be found there. Volcanoes and earthquakes are most likely to occur where we have 2 tectonic plates pushing against each other and they collide with each other, thus forming some mountain regions as well. And then what happens usually is one of those plates will subduct or go below the other and start to melt, and that's where we get the magma that is found in volcanoes, and that's where we get our big collisions that form our earthquakes as well. Plate boundaries can also have dramatic features. When we get 2 continental plates colliding with each other, we usually get huge mountain ranges, and then we usually have rift valleys form where they start to pull apart or away from each other. The mid-oceanic ridge is going to result from divergent boundaries. So those are going to be boundaries that pull away from each other, or move away from each other. A divergent boundary usually will have new rock that forms, and it's going to be forming from magma that comes up, cools, and then pushes those plates apart from each other. That thus forming what we call the divergent boundary. Usually at these divergent boundaries, you will find your rift valleys. Okay, so if you look at the picture here, the rift valley is going to be usually at the bottom of the ocean, where it's going to be a narrow valley, forms from the tectonic plate, magma comes up out of the asthenosphere, it starts to cool on the ocean floor, thus pushing the plate further away from each other and moving them in opposite directions. Next is going to be the other type of boundary is going to be known as a convergent boundary. Convergent boundaries are going to be when we have oceanic plates usually colliding with continental plates. What happens at this is they both collide together, and one of those plates, usually the oceanic plate, is going to slide underneath the other. This point in which the oceanic plate subducts or goes below the continental plate, this is known as the subduction zone. Or what subduction is once again where the process in which one of those lithospheric plates, or one of the plates, is going to collide with another and thus go below it. Usually what you find at these subduction zones are going to be trenches, some deep drop-offs in the ocean. If you were to go out swimming in the ocean and there's a deep drop off, that's where the oceanic plate has collided with the continental plate and is subducting. You usually find just on the terrestrial or the land side of that, you'll usually find huge mountain ranges and even some volcanoes as well that will form. So here's what convergent plate boundary looks like. You have the oceanic plate on the right side. It's colliding with or pushing towards the continental plate. It will then dive down below the continental plate. And so what you'll find is just off the beach there, you usually find a huge drop off known as the trench, or in this case, the ocean trench. And on the continental plate, you'll see those mountain ranges start to develop and get pushed up because this rock, as it goes down, is going to push the continental plate up. And it's also going to start to melt, and that's where the magma will start to build up and form our volcanoes as well. So when we get these oceanic crusts generating our volcanoes, once again, the upper plate, in this case of the subduction zone, is going to usually form chains of volcanoes that take place along those mountain ranges. Those mountains or the volcanoes can actually form far inland as they are still associated with that oceanic trench and this subduction process. Islands may form from these oceanic plates meeting, and magma can then rise to the surface. It may form what we call an island arc. And if you've seen Alaska, those islands there off the tip of Alaska are going to be known as an island arc. Colliding tectonic plates thus create mountains, and what we'll find at those mountain ranges is usually huge mountain ranges taking place like the Himalayas, where we have two tectonic plates or two continental plates colliding with each other. The third type of boundary is going to be known as a transform boundary. What can happen at these transform boundaries is our plates are actually going to slide past each other and crack the earth. The plate movement at the transform fault boundary is going to be one that causes large earthquakes. Usually what happens along these boundaries is we'll have a fault line. One rock that has pressure on another rock, and what will happen is eventually that pressure gets moved or they grind past each other, and there's going to be a large movement or jut in the plates, and thus creating large earthquakes resulting from that. So when we talk about a fault is usually going to be a break in a body of rock along which one block slides past the other. And this is where we get our huge volcanoes. So what you usually find in faults is two plates that were connected to each other. Maybe they were pushing up against each other or sliding past each other. But when that plate gives and one slides past the other one, the foot wall and the hanging wall, what happens is we usually have large earthquakes sent out from those regions. Okay, so that's your notes for today. Hopefully you were able to fill out your assignment and get that turned in. We'll see you on the next one.